All right, I want to welcome everybody to our fifth lecture here for Organic Chemistry 51C here at UC Irvine. Again, it's the second week of the spring quarter during this coronavirus health issue that's going on. And so we're giving all our lectures remotely. And I will start by talking about something that I've seen that sparks my curiosity. And I'm always curious about organic chemistry. It's so interesting. And what I saw was this article that's referring to the Mars Curiosity rover and the fact that they have discovered organic molecules on Mars. And so let's get and talk about that. There's something cool about this. I saw a lead article by Paul Scott Anderson that mentions a class of molecules called thiophenes, which I'm not sure was discussed much or at all in the chapter on aromatic compounds. Let's go ahead and talk about thiophenes. What are these molecules that they discovered on Mars? So the Mars Curiosity rover can drill into the ground. I've got this little picture here, and it has this whole suite of equipment on there for analyzing samples from Mars. And one of those allows it to heat up those samples in order to volatilize any organics that might be on there. And the heating conditions are kind of strong. So they heat somewhere between 500 and 800 degrees. Stuff decomposes, chemistry happens, organic compounds are released from the middle of the rock, maybe even chemically changed. And there's a mass spectrometer on board the Curiosity rover, just like the mass spectrometry that we use here on the planet Earth to analyze organic molecules. And they tell you molecular formulae, mass to charge ratios. And after doing this analysis, they were able to show that, that after heating and doing mass spectrometry, that they were able to identify a variety of different thiophenes. Thiophenes are aromatic 5-membered rings where there's a lone parent sulfur, so that makes 2, 4, 6 electrons, 6 electrons aromatic rings. These are aromatic compounds. They have clear, convincing evidence of thiophene, this parent compound, and these 2-methyl and 3-methyl thiophene compounds. You can exactly match the mass spectra, just like we match them up on Earth to libraries of mass spectra. What's more, they also said that they identified another molecule that they said was presumably benzothiophene. And unfortunately, in that news article, they drew, or in this publication, they drew the structure of benzothiophene in this way, down below here. And unfortunately, that's like somebody telling me that I'm looking at a picture of a person, but their arm is coming out of their head. There's something obviously wrong about this. This is not the benzothiophene that's stable or that you see in any common circumstance, because they've fused the benzene ring onto the wrong side of the thiophene. Over here on the right is the structure of the normal benzothiophene, the ones that's stable. And the reason why this left-hand side benzothiophene is not a plausible structure for a stable compound that's produced at 500 degrees is that you don't see 3 double bonds in this 6-membered ring. Over here on the right-hand side of this 6-membered ring, you're missing a double bond. There's 2 double bonds sticking off of the edges. And we refer to that as cross-conjugated. That means this benzene ring, this 6-membered ring, is not a benzene ring. It's what we refer to as cross-conjugated, and that means it's not aromatic, and that means it's not very stable. So I think what they intended to draw was this other benzothiophene, the aromatic form, where the sulfur is directly attached to the 6-membered ring instead of isolated over here. And this is fully conjugated, fully aromatic. That's the form of benzothiophene that they were probably detecting, if they were detecting one. I think it's cool. They're detecting thiophenes on Mars. There's organic molecules on Mars. Who knows whether there was ever life on the planet Mars, or possibly now. Always cool to see organic molecules out there. So the chapter is about this. It's about, here's a bunch of compounds with oxygen and H's on them, and how easy is it to pull that proton off and leave an oxygen without a proton there? And the way you determine that is you go to a table, or you type up in Google pKa and the name of the compound. Type ethanol and pKa, and you'll find out that ethanol, water, isopropanol, they all have pKs right around 16. Now, do I care whether it's a 15.74 pK for water versus 16? No, I'm not that smart. They're all about 16. That's good enough for me. So any alcohol or water has a pK of 16. Phenols are more acidic. Phenols have pKs of 10. And then we come down to carboxylic acids. It still to this day bothers me that more acidic means lower pKa. That seems like it's just designed to screw you up. I feel like somebody should have invented a system where higher pKa means higher acidity, but I didn't make up the system. We're stuck with that, and it's going to seem backwards to you. And it's probably going to mess you up at some point. But lower pKa means more acidic. Finally, we get down here to a real powerful acid, para-toluene sulfonic acid. And we'll be using this more coming up in later chapters as an acid catalyst. Look, it's super cheap to synthesize para-toluene sulfonic acid on an industrial scale. They take toluene, which is an industrial solvent, and then they sulfonate it using sulfur trioxide and sulfuric acid. But it's super acidic, and it's about as acidic as sulfuric acid. This is one of the most acidic reagents, certainly the most acidic mineral acid that we have in my laboratory. And it is a super powerful acid. I don't think we're going to talk about any more powerful acids than this in Chemistry 51C. Now, what's important to memorize here or to learn is that pKa is log units. So when I come over here and I look at the difference between phenol and acetic acid is more acidic than phenol, not by 5 times, by 10 to the 5th. These are exponents. So if I rate everything relative to a water or an alcohol, and I give that a relative acidity of 1, that means phenol isn't 6 times more acidic. It's 10 to the 6th more acidic. It's 1,000,000 times more acidic than an alcohol. And if I take a carboxylic acid, right, that's now 10 to the, it's 11 orders of magnitude difference. I don't even know how many zeros, let's figure out how many zeros that is. 11, there we go. 11 zeros. Am I getting to 11? Does it even matter how many zeros I've got? Acetic acid is so much more acidic than an alcohol. You should never ever make a mistake of thinking that this OH bond is if it's 100 billion times more acidic, right? If I offered you $1 or $100 billion, you wouldn't have to think hard about which one you want. So I'm mystified sometimes how people can mistake the acidity of a carboxylic acid for the acidity of water. When you deprotonate those anions are not equally stable. And finally, we get down here to powerful acids, these organic acids or inorganic acid, a mineral acid like sulfuric acid or toluene sulfonic acid. Why would you use one over the other? It's because toluene sulfonic acid is a solid. Sometimes you just need to weigh a few milligrams out on the balance, and that's easy. Sulfuric acid is this goopy liquid, and you can't just easily weigh a few milligrams of a goop. So that's why organic chemists love to use toluene sulfonic acid. And if I draw this, again, this is so many zeros here. Relative to water, that's what? I don't even know. I'm not good at math. How many orders of magnitude different is that? Like 16 plus 10 to the 23? The difference in acidity between this and water is so dramatic. So I hope as we go into this chapter here that you'll get the difference in acidity between sulfonic acids and water, or even a sulfonic acid and acetic acid. In later chapters, they're going to say, oh, put in this amine with mild acid. And I don't know why, but they don't just tell you that the mild acid is acetic acid. It seems kind of crazy to me that they don't want to tell you the name. But this is why they would call this a mild acid, acetic acid, is because compared to sulfuric acid or hydrochloric acid, that's mild. Hydrochloric acid has about the same acidity but this chapter is about oxygen-based acids. But I'll just tell you, this is about the same acidity as hydrochloric acid. It's pK of -7. Those are powerful acids. So, and just coming back to this water, you know, that doesn't look very, you know, sure, in water you've got a small amount of the deprotonated form, like 10 to the minus 7 molar, but really nothing in terms of acidity like acetic or toluene sulfonic acid or sulfuric acid. All right, that's what we're going to be working on when we come back on Wednesday. We're going to be talking about the acidity of OHs. I'm going to ask you to understand equilibria. Like if two species are fighting it out for a proton, which one wins? They're not all equally acidic, right? The differences are so huge that if you memorize pKa's and forget that they're log units, you'll forget how very, very different these are in terms of acidity. And I don't want you to forget that. All right. You know, the start of almost all the chapters in the organic chemistry textbook talks about IUPAC nomenclature, how to name compounds. And as a chemist, I'm proud we have IUPAC nomenclature, because if you look at the names of biological macromolecules, the names that come from geneticists and biochemists are not systematic, and so can be pretty frustrating. But I don't ask IUPAC nomenclature on any of my exams or any of my problem sets. I don't give you a long IUPAC name and say, draw the structure. I don't draw the structure and tell you to give me an IUPAC name. We have programs, synthetic organic chemists have programs that we use, mainly ChemDraw. That's what I use to draw all my structures, that you circle the structure and say, what's the name? And it gives you the IUPAC name. But what I am good at, and what every organic chemist is good at, is naming functional groups. So I expect you, when I tell you to circle the carboxylic acid, I expect you to know what I'm talking about. When I say, here's 5 compounds, draw a box around the phenol compound, I expect you to know which compound is a phenol. So I expect you to know the names of functional groups. Now there are a few, I'm not sure if they're still doing this, there have always been standardized exams like the MCAT, the DAT, that ask you IUPAC nomenclature. So I encourage you to look at that section and become familiar with IUPAC nomenclature. So you're surrounded by carboxylic acids everywhere, but sometimes they're in disguise. And I've drawn a little ingredients list from a package of chips or crisps if you're in the UK. And you can see that some of the carboxylic acids are clearly indicated on the ingredients list. Malic acid, citric acid, but this package of chips or crisps contains more carboxylic acids than this, but some of them are in disguise. So for example, sodium acetate is actually a carboxylic acid in disguise. Monosodium glutamate is a carboxylic acid in disguise. Let's go ahead and take a look at the chemical structures of these and how those names relate to carboxylic acids. So I'm going to go ahead and draw the structure of acetic acid. That's the simplest carboxylic acid in this ingredients list. And we'll talk about what is those disguised names. So this is acetic acid. Acetic acid. I think the IUPAC name is something like ethanoic acid, but nobody really uses that. And I'm going to draw out an equilibrium between acetic acid and its deprotonated form. And so I'll just, I'll go ahead and draw out hydroxide as a base, so we can just talk about this simple acid-base equilibrium. And if you treat acetic acid with sodium hydroxide, this will deprotonate the sodium hydroxide and leave you with the deprotonated form that now carries a negative charge. I'm going to draw all the lone pairs on this oxygen since it's got the minus charge on there. And it gives you water as a byproduct. That's not really the important byproduct in that reaction. And the sodium is still hanging around. Those will end up forming a covalent bond. And let me go ahead and add some arrow pushing. I don't think the arrow pushing for deprotonation of a carboxylic acid by a base is that exciting, but I can't resist drawing that arrow pushing in there. So the name for this species is sodium acetate, sodium plus this acetate anion. So let me go ahead and draw that name down there. That's what they're putting into these chips, into this bag, into the crisps or chips that are in that bag. And we would refer to this species over here as an acetate anion. So this species without the sodium is referred to as an acetate anion. And that's the kind of naming I expect you to be good at. I don't expect you to know that this is ethanoic acid or ethanoate, but I expect you to know that this is a carboxylate functional group. Over here, you can see malic acid in the ingredients list. If you had the deprotonated form of that, you would call it malate. You can see down here it contains monosodium glutamate. That's the monosodium salt of glutamic acid, one of the amino acids that gets incorporated ribosomally into proteins by all organisms on the planet Earth. Let me just go ahead and draw up the chemical structure of glutamic, well, not of glutamic acid. I'm going to draw the chemical structure of monosodium glutamate. Normally, glutamic acid has a carboxylic acid side chain with an OH over here, but monosodium glutamate has been deprotonated with sodium hydroxide or some sodium-containing base, and this is the chemical structure of monosodium glutamate. Glutamate, this species called glutamate, is a neurotransmitter in your brain. It's important for memory, long-term potentiation, and some people are under the mistaken impression that this enters your brain somehow, and in a non-equilibrium fashion that's not controlled and causes headaches. I'm not sure if there's any evidence for that. Okay, so I don't really expect you to know IUPAC nomenclature for my exams. It's great to know that. I do expect you to know what a carboxylate functional group is, or carboxylates, or carboxylic acids that have been deprotonated. Section 19.3 is on properties of carboxylic acids, physical properties like polarity, or so. I'm not going to ask you those questions on my exams. I'll tell you the main thing I know about carboxylic acids is they taste sour. So that's what makes lemons taste sour, vinegar tastes sour, make foods taste sour. And when you deprotonate them, they become water soluble. So usually in drugs that you take in the form of pills or in foods, they're quite often deprotonated, like sodium acetate or monosodium glutamate, because that confers water solubility when they have a charge. Okay, let's go ahead and talk about spectroscopy. You know, I think I always ask about one spectroscopy question on my exams. I'm not going to promise anything I'm going to do on my future exams, but if you look at my past exams, I've always asked one spectroscopy question because we expect you to learn something about spectroscopy, whether you're going on to medicine and doing magnetic resonance imaging, or going into astrophysics and studying planets using spectroscopy. So what do I really expect you to know about carboxylic acids? There's one type of spectroscopy that's reasonably diagnostic for telling whether you have a carboxylic acid. I would say that the most useful, the most reliable form of spectroscopy for knowing whether you have a carboxylic acid is proton NMR. Usually we don't plot proton NMRs past 10 parts per million. Almost always you end up with this spectrum that is just 10 to 0, and all the interesting stuff is there. Every once in a while, somebody will give you a spectrum that goes past 10 parts per million, and there might be one peak in there, not more than one. That would be completely unusual. And if somebody ever gives you a spectrum that goes past 10 parts per million, they're kind of telling you you've got a carboxylic acid or an acidic OH. So that's in this region, right? Only acidic OHs, usually carboxylic acids. Every once in a while, you'll see a phenol that is so acidic because it has the right functional groups that it pushes the OH down in this region. But you don't. These are almost always carboxylic acids. I don't want to say always, but almost always carboxylic acids are occurring above 10 parts per million. And moreover, those are usually broadened. So instead of being tall, thin, sharp needle peaks, they're small, flat hills that still have an area under the curve of 1, but they're kind of broadened. So this region of like 10 to 12 parts per million, that's usually somebody's telling you there's a carboxylic acid in there. It's an acidic OH is really the reliable thing. Now, what if you've got an acidic OH in your compound? I would next look at my IR spectrum, because any kind of acidic OH is good at hydrogen bonding. And there's like, once you put things in solution that can hydrogen bond, they're forming hydrogen bonds, they're breaking hydrogen bonds, they're hydrogen bonding with 10 different neighbors, and that causes a whole range of frequencies. So you end up with this huge lump, this big-ass lump in your spectrum that is usually suggesting that there's something that's fantastic at hydrogen bonding. And OHs, maybe I shouldn't have picked this example, because usually that OH stretch will just dominate the entire spectrum. It's so strong at absorbing. You could also have acidic NHs that look pretty big, but the biggest and lumpiest are carboxylic acids. Those are the best at hydrogen bonding. So these kind of take over the entire spectrum in this whole region where all the CHs normally appear, the OHs, the NHs. Carboxylic acids are so much more adept at hydrogen bonding than alcohols. Phenols, slightly less so. Okay, I would say it's also useful to look at the C13 NMR. If you've got a carboxylic acid, what you should be looking for is a carbonyl carbon that's past 160 ppm. So I'll give you a range. It's about 190 to 155 parts per million. That's the carbonyl stretch region. So in that region of the spectrum, that's usually where you find carbonyls. There's a tiny bit of overlap with aromatic compounds up to about 160. But when I see this, I know it's a carbonyl. Unfortunately, I don't know whether it's an ester. I don't know whether it's a carboxylic acid. I don't know whether it's an amide. I don't know whether it's a ketone. I don't know whether it's an aldehyde. I just know it's a carbonyl. So I would have to back that up, usually by going right to the proton NMR to be clear about what kind of carbonyl compound is it. Because if you see a carbonyl, one single carbonyl peak, and then this peak past 10 parts per million, you've got a carboxylic acid. So again, lots of things have carbonyl groups. So you can't tell from the C13 spectrum alone that you've got a carboxylic acid on your hands. Okay, let's go ahead and take a look at this process of equilibrium, and what is it that makes something acidic? There's one big effect that can really confer acidity. So if I ask you to judge the acidity of some oxygen-containing compound with OHs, I'm looking for something. I'm looking for a particular characteristic here. An OH compound, whether it's a carboxylic acid, whether it's a phenol, whether it's some other OH-containing compound, an enol, we'll talk about those later. An OH compound will be very acidic if and only if the RO- species, if and only if once you deprotonate it, that species is somehow very stable. And so when I ask you questions, like oftentimes I ask you to rank the relative acidity of these 5 OH compounds. That's a common question I would ask. It's a common question other instructors might ask, or exams or sapling homeworks, or what they're really asking you to do is redraw the conjugate bases and rank those in terms of stability. You can't just look at the acids and decide. You have to somewhere else on your page draw out the conjugate bases and then decide for yourself which one is being most stabilized. And the biggest effect that makes things acidic is resonance. So let's go ahead and talk about how that comes into play in determining the relative acidity of these compounds. So if I ask you to compare these 2 compounds, or 4 compounds, or 12 compounds, and I asked you to compare the acidity, you really need to start off by drawing out the conjugate base. What would happen if you deprotonated that? You know what kills me is that the value that you get from titrations, titrations are easy to do. It's easy to determine how acidic something is, are pKa's. And it always kills me that things that are more acidic have lower pKa's. That always seemed backwards to me, and it's always seemed to throw me off. And you just have to get used to that. More acidic, lower pKa. So, and we talked about pKa's on Monday. Okay, so let's go ahead and take a look at the conjugate bases that result from deprotonating of just a regular alcohol like ethanol versus deprotonating a carboxylic acid like acetic acid. There we go. There's the conjugate bases. Now, when I look at these, I can't really make any decisions about how acidic these are by looking at the OH compounds. What I have to do is look at how stable these oxygen anions are. They're both oxygens. They both have negative charges on oxygen. But what's different and what's exceptional is that I have awesome resonance here with this carboxylate anion. Let me go ahead and use some arrow pushing to draw out that resonance structure. I can use this lone pair to attack the carbonyl and donate those electrons in and draw a great looking resonance structure that also has negative charge on an oxygen atom. Oxygen's electronegative. And so this great resonance, let me circle the charges so it doesn't look like a, sometimes I circle the charges to make it more obvious. I don't always do that. So here's two fantastic resonance structures. So acetate anion, unlike ethoxide, is resonance stabilized. And in both of those resonance structures, I'm running out of room on my page. I just fit that in there. In both of those resonance structures, I can put negative charge on electronegative atoms. That's fantastic. That means those are good resonance structures. If in each resonance structure, I can put a negative charge on an electronegative atom, that tells me that this extra resonance structure is really good, if I can also put a negative charge on an electronegative atom. So I've got this great resonance stabilization for the anion that I didn't have for the simple alcohol, this alkoxide anion. So that tells me that this is going, the carboxylic acid is going to be more willing to give up that proton and become negatively charged. You can't just look at the OH forms to decide which is more acidic. You've got to get used to drawing out the conjugate bases of these in order to address this issue of acidity. You know, the result of this, right, once you look at these deprotonated forms, is that this carboxylic acid is about 100 billion times more acidic, right? Again, if you do it in log units, 11 pKa units, it doesn't sound like much, but when you really draw it out as a regular numeral, you can be more impressed by how much acidity you get from being able to resonance stabilize that anion form. So when I ask you to judge the acidity of compounds, even if it doesn't look like there's much room on the page, you need to draw out the conjugate base forms and decide which of those is more acidic. So this chapter on carboxylic acid, on really the acidity of OHs, is not just carboxylic acids, because we also have resonance that's present for phenols and phenoxide anions. So let's go ahead and talk about phenols. So if I ask you to compare the acidity of these two species, cyclohexanol and phenol, those are not equally acidic. They're not even close. You know, the phenol is 100,000 times, not 100 billion times, but it's 100,000 times more acidic than cyclohexanol. And so to understand why, let's go ahead and draw out those conjugate bases that you would get. So if you deprotonate cyclohexanol, don't think you're going to have some shortcut. You just draw out the conjugate bases. There we go. We're asking about how much this wants to donate the proton, so we better figure out what it looks like after it donates the proton. If cyclohexanol acts as an acid and gives up its proton to something, it's going to have a negative charge on oxygen, and that's pretty good. But over here, with phenol, it's even better. So let's go ahead and talk about how much better that is. And again, I have this negative charge on an oxygen atom, that's great. But in addition to having an oxygen charge on an atom, I can start drawing resonance structures for this. Let's draw some of these resonance structures and think about how resonance stabilized this phenoxide anion is. So let me go ahead and draw out the resonance structures I would get. There's going to be more than one resonance structure. You should be used to drawing resonance structures based on aromatic compounds. And you might be thinking, oh man, not another one of these chapters where I'm drawing resonance structures of rhenium ions and benzene rings. You just have to do it. Quit whining and just start drawing out resonance structures. And the time it takes you to whine about drawing out these resonance structures, you probably could have drawn them out. So my arrow pushing tells me I'm going to leave a negative charge on the ortho position next to this oxygen substituent. And this is not this resonance structure is not great. It's not, we'll talk about this in just a second. Let me keep going because there's more resonance structures I can draw kind of similar to this. I can take this carbanion ortho to the oxygen, and I can donate it over here. I could either make the arrow end on this, in the middle of this bond here, and make us to show that I'm making a pi bond, or I can make it attack this carbon atom. I just want you to be precise about which of those two you choose, so I can clearly see. Don't do it halfway. Either attack the atom or make your arrow end in the middle of the bond. Those are both acceptable ways. And let me break that pi bond and give the electrons over here to this carbon atom. So when I draw out this next resonance structure, right, resonance structures are double-headed arrows. Don't draw equilibrium arrows like arrow forward, arrow backward. That's not what we're drawing. We're just drawing different depictions of exactly the same species here. So here's yet another resonance structure. It looks like a carbanion. There we go. I don't know why I chose to circle that, so I better circle all the others. Sometimes I circle my negative charges, sometimes I don't. There's one more resonance structure I can draw, or I take this lone pair and I donate it in and put it on the other side of that carbonyl oxygen, or of the oxygen substituent on the benzene ring. And I've kind of reached the end of the road here for my resonance structures, because if I push again and put the electrons back on the oxygen, well, I'll be right back here. So I'm not going to draw that again. So there's 3 additional resonance structures in addition to this original O- resonance structure. Now let's talk about these. How good are these resonance structures? You'll notice that none of these resonance structures put negative charge on carbon, and carbon's not very electronegative. I'll just put this here, negative charge on carbon. That's not so good. So in that sense, these are not really great resonance structures. But let me point out, any structures that have CO pi bonds are actually good. CO pi bonds are more stable. I'm not even sure I could fit this in, are more stable than CC pi bonds. So that's good. But the other downside of this is I've lost aromaticity. These are not aromatic, right? You can't count up, unless you have a double bond somewhere in this ring, you've lost, all of these structures are non-aromatic. So I've got 3 resonance structures. There's 3 of them. I'm kind of distributing the negative charge on 3 carbons. That's good. So even though carbon's not very electronegative, at least I'm not putting it onto just one isolated carbon atom. The CO pi bond here makes these good, somewhat good resonance structures, but the fact that they're not, I've lost aromaticity in all of these resonance structures kind of sucks. There's one more resonance structure I did not draw that's not very interesting, and that's just simply shifting around the pi bonds in the benzene ring. That doesn't really explain the acidity of why this O- is stable. So on balance, all of these effects together make it so that you're not stuck with the negative charge on one oxygen. You can distribute that negative charge to other atoms, and as a result, you get 10 to the 5th more acidity. The pKa's of these species, the pK of an alcohol is about 16. The pKa of a phenol is about 10. You can use sodium hydroxide to deprotonate phenols. Just put a phenol in 1 mole of sodium hydroxide and it'll be soluble and charged and go into the aqueous layer. Okay, so we expect you to be able to draw these types of resonance structures when you think about the acidity of phenols. So let's see how you might do that, because it's kind of boring to do it with phenol that has no substituents. We're not going to ask you about stuff like that. The kinds of questions that you're going to get in our homeworks, the kinds of questions you're going to see on exams, will ask you to consider the acidity of substituted phenols. This is like an extravaganza of resonance structures where you just have to get used to drawing lots of resonance structures. Let's go ahead and draw out some of the resonance structures here. Let's start by drawing out, if I ask you to compare, let me just say, compare the acidity of these 2 phenols, then you just need to start off by drawing out the conjugate bases. So here's these conjugate bases. Here's the conjugate base just for phenol. There we go. And then down over here, I'll draw this orthonitrophenol group. We're going to have to draw out that nitro group in a second, but for now I'm just going to use the text abbreviation NO2 here for this phenol. Sorry, I didn't do a good job with this pi double bond there. You know, I don't have to draw the lone pairs on here. I'm not sure how to describe this. Whenever I draw a charge on an atom, I feel this compulsion to show everything that's attached to that atom. Like if I make a carbocation, I feel like I want to draw all the substituents, even if they're H. When I put a minus charge on an atom, I feel like I want to draw all the lone pairs and all the attached atoms. It's just a compulsion that helps me to see what I'm dealing with. Okay, so we've got lots of resonance structures to draw here. So let's go ahead and get started. Let me go ahead and draw some resonance structures. And the first resonance structure I'm going to draw, I'm going to go ahead and push these electrons up over here. And as soon as I push the electrons to this carbon, I'm going to have to break this pi bond. I can't have 5 bonds to that carbon, and then I'll leave the electrons next door. Now, I could keep pushing it, but I'm going to try to draw each one of these resonance structures in turn and make the first resonance structure end with the carbanion right next to that nitro group. And this time, since it's going to leave a carbanion right next to the nitro group, I'm going to draw out the Lewis structure for that nitro group because obviously it's going to have some influence on a carbanion. Let's try to judge what that influence is. Let me go ahead and draw out. So here's my carbanion, and here's my nitro group. For the nitro group, I can make the O- on the top or on the bottom, but look at this. I've got this N+ right next door to this carbanion. So I'm going to be able to draw a particularly good resonance structure with that. Let me start off by pointing out that whether it's phenol, whether you have a nitro group there or not, I've got all these other resonance structures just like before. But all these types of resonance structures, if I donate, I don't want to put the arrow pushing here because I'm afraid of having two different sets of arrow pushing. You know, we're going to have those same 3 resonance structures that we talked about on the last slide, where I can push that negative charge over here to the para position from the oxygen, and I can push that negative charge again to the other ortho position next to the oxygen. But I could do those same resonance structures whether there's a nitro group or not. So the nitro group doesn't change any of these 3 resonance structures. I could do the same thing for phenol or the phenolate anion. I'm just not going to do that for the phenoxide anion. But what I want to do is I want to draw the one important resonance structure that I can't draw for simple unsubstituted phenoxide. And that is to push the electrons from over here right into that nitro. I don't want to make a 5th bond, so I have to break one of the bonds to this nitro group, and I'll break this bond. And that resonance structure immediately looks satisfying to me because it means that I'm putting that extra negative charge on an electronegative oxygen atom. And that's great. Uh-oh, I'm kind of running out of room here, so let me try to angle my nitro group up a little bit here. This was not well planned on my page. Oh man, I'm running out of room. Here we go. There's that oxygen. There's that negative charge. The N is still positively charged. We don't get anything special for that. So I have this resonance structure that puts negative charges on the electronegative oxygen atoms. That's where you want to have negative charge, is on electronegative atoms. Fluorine would be best. There's no way to put negative charge on fluorine. Oxygen is the 2nd most electronegative atom in the periodic table. That's awesome. Look at that. So that's great that this is a particularly good resonance structure, and because it puts negative charge on electronegative oxygens. I can't fit the word oxygens in here. I'll put oxes. Oxes, there we go. That's great. Wow. So, you know, as a result, just having that nitro group on there, this compound, ortho-nitrophenol, is 1,000 times more acidic than just plain phenol. And it's way more acidic than cyclohexanol or water or alcohols. But just compared to phenol, it's 1,000 times more acidic. Comparing these 2 structures here, that nitro group at the ortho position. So look at all the resonance structures I had. Really, this is the only important one. These other ones I could also draw for phenol, for phenoxide anion. I'm not doing that. You know, these other resonance structures, you know, of phenolate or phenoxide, depending whether you use newer or older nomenclature, you know, those don't really explain the difference of having that nitrate. It's this one resonance structure here. That's the one that tells you the difference. Okay, so resonance has the biggest effect on the stability of O- compounds. It's the ability to draw resonance structures. If you want to explain big differences in the acidity of OH compounds, you know, 1,000-fold, 10,000-fold, 100 billion-fold differences in acidity, that's resonance. Let's talk about another effect that's not resonance, that has smaller effects, that the book totally overblows in a disappointing way, these extra effects. So there's another effect, and that's called inductive effects, and in some books they call it a polar effect. And these are slight effects, up to maybe 10 to the third. You know, or, you know, if you're talking about factors of 2, 3, 5, 10, 100, those are not huge effects. But we're going to talk about it because the book makes a big deal about these. Maybe they think it's more obvious to you because you can see everything in front of you. And so we're going to talk about this difference here. It's a factor of 100 difference, which isn't very much. The book makes a big deal about the fact that chloroacetic acid is more acidic than acetic acid. So that chlorine atom has an effect here, a factor of about 100, not much. So if we want to talk about differences in acidity, we've got to talk about the conjugate bases. I'm going to draw the conjugate base of chloroacetic acid. I've already drawn the conjugate base for acetic acid before. So let's go ahead and draw out that conjugate base. So I'll go ahead and draw this over here. There we go. That's the chloroacetate anion. So what effect, if you're thinking about this equilibrium process here, how much does this enjoy having that O- versus acetic acid having an O- on there? There is an effect here, and the effect that the chlorine has is caused by the fact, let me go ahead and put this in green just to distinguish this, is that the chlorine atom has maybe a partial positive charge. It's a polar effect. Chlorine atoms have more protons in the nucleus, but it's also a bigger atom, so those positive charges in the nucleus are shielded a little bit. So it is electronegative. It's not anywhere near as electronegative as fluorine, which is a second row atom. So there's this effect here. It's a polar effect. There's no resonance. So that electronegative atom there, so electronegative chlorine, wow, you know, I'm thinking, hope I didn't make a mistake here with my atom, because this pKa seems awful acidic. I hope I didn't mistakenly draw chlorine when I meant fluorine. I'll have to check back on that later. So an electronegative chlorine atom stabilizes that oxygen. You'd also see, I have to go back and look to see if I misdrew, and maybe this is a fluoroacetic acid when I accidentally drew the chloroacetic acid. But whether it's fluorine, let me just say electronegative halogen atom, and I can worry about the actual quantity later, that the electronegative halogen atom stabilizes the negative O- through a polar effect. It's kind of like through space. Like there's a negatively charged atom over here on the other side of the universe, right, or somewhere nearby, and I have lots of protons in my nucleus, lots of positive charge. And so there's this Coulombic type stabilization. Now you might be tempted to think, oh, what's Dave talking about? Aren't there lone pairs on that chlorine? And can't I somehow draw some resonance structure some way? No, there's no resonance involved here. There's a saturated sp3 carbon atom right here. And you can't push any resonance structures that bring you anything from the chlorine over here to the O-. So let's just be clear, there's no resonance that's involved. So no resonance is involved here with these types of what's called inductive effects. It's not a resonance effect. Resonance effects are big, 100 billion, million. Those are big effects. What happens if we put 3 chlorines on here? Well, it's a bigger effect. I just happen to know the pKa's because it's easy to get pKa's by doing titrations. You probably did titrations in high school. So if you have 3 of these, you know, you get about 1,000-fold effect here. It's 1,000 times more acidic, but 10 to the third is not huge. 10 to the ninth is huge, not 10 to the third. Or if you move the chlorine even farther away from that carboxylic acid group, well, the effect turns out to be so small, it's not even a factor of 10. I mean, we don't spend a lot of time dilly-dallying and worrying and wringing our hands over, 2 times faster or 3 times faster. We're interested in 100 billion times faster. And of course, if we bring that chlorine even farther away, this is essentially this is so close to indistinguishable, these pKa's. So, as the chlorine gets farther, or fluorine or bromine, even less of an effect, as you get farther and farther away, this is not, the effect is subtle and it's real, and it has nothing to do with resonance. These are polar effects. If I put an ammonium ion nearby, you may think, oh, I've seen carbocations. You can have resonance. That's not a carbocation. I can't donate any electrons into that N+. It's already got 8 electrons. The problem is not that it doesn't have enough electrons. The problem is it's sharing its electrons with too many neighbors. So when you look at the pKa of this is glycine, the protonated form of the amino acid glycine. This is actually, whoops, let me put it in red. I didn't mean to mistakenly draw in black there. This is a pKa, it's like 100 times more acidic, about 2 log units more acidic. So having a straight up positive charge leads to a pretty big polar or inductive effect there. But it's nothing like resonance. Again, the effect here has nothing to do with resonance. Let me just draw these H's here. You may think that if you drew out the conjugate base, like I tell you is important, that somehow you're going to be able to draw a resonance structure to explain this effect. There's no way. There's no resonance structure you can draw here that will ever make that N+ disappear. No resonance structure. The only resonance structure you can draw is to push the electrons up to the top oxygen. And you can do that with any of these carboxylic acids. Okay, inductive effects slightly enhance acidity. Again, because you can see every atom involved in an inductive effect and you don't have to draw those bothersome resonance structures. The book loves these and asking you about these, but they're small. I'm kind of sorry they waste so much time. They ought to be spending their time asking you about resonance effects and their effect on negative charges. Okay, let's go ahead and talk about acids and carbonyls. It's kind of confusing, and I'm going to tell you something different. When I see a carboxylic acid, if you're like me, you're probably thinking, oh yeah, well I want to make the carboxylic acid protonate something. But what we're going to see coming up in a couple of chapters, maybe 3 chapters from now, chapters 21 and 22 in the 5th edition of the Smith textbook, we're going to see that you can protonate a carboxylic acid. You can add a proton to a carboxylic acid. Do you remember this recipe for nitration where we used nitric acid? And then we put in sulfuric acid in order to protonate the nitric acid. It turns out this type of process is really important for making substituted carbonyls. Let's go ahead and take a look at this. So if I take a carboxylic acid, which has a pK around 5, and I put in a really strong acid, crazy strong, sulfuric acid that has a pK of -9, not +9. This has a pK of +5 over here for the carboxylic acid. Sulfuric acid is 16 orders of magnitude more acidic than the carboxylic acid OH. If anything is going to donate a proton in here, it's going to be the sulfuric acid. This OH is not going to do anything as long as there's a sulfuric acid around. Let's go ahead and draw what would happen here. And note that I'm going to use the lone pairs over here on this carbonyl oxygen. We'll talk about that in just a minute. And you need to get used to this process. You're going to see it over and over again in later chapters. Take that carbonyl oxygen. You're going to see this with ketones. You're going to see it with aldehydes. You're going to see it with amides. You're going to see it with esters. You're going to see it with cyclic esters. You're going to see it with lactones. Get used to it. Even though there's a carboxylic acid here, if I put in a really strong acid, like sulfuric acid or hydrochloric acid, those are the common ones, then I'm going to see an acid-base equilibrium reaction. I'll draw the reverse arrow, but it's not a particularly strong reverse arrow. So you end up with this extremely stable sulfate anion, and then you end up with this protonated carboxylic acid. And we'll go ahead and talk about that. And you end up with a proton over here on the carbonyl. Whenever you see 3 bonds to oxygen, you would call that an oxonium ion. So once you put a proton in here, it's still acidic. You know, it wants to go back. The lone pairs on sulfate will grab it and it'll go back. And then the sulfuric acid will protonate the carbonyl and it'll go over here and go forward. And then the sulfate will pull it off and it'll go back. The equilibrium lies on this side. The pKa of this protonated carboxylic acid is about -6. So there's 3 orders of magnitude difference between the pKa's of these. And that means the equilibrium is about 1 to 1,000, 1 to 10 to the 3rd. So the equilibrium, for every 1,000 molecules of acetic acid in here, 999 of them are protonated on this oxygen on top, and the other one is just kind of sitting there. It's at equilibrium, it's 1,000 to 1. And I get that just from knowing that the pKa's are 3 log units difference. Now, why do we protonate the top oxygen instead of the bottom oxygen? And let me show you why. Let's go ahead and draw this. We've got a great resonance structure we can draw here, where we take lone pairs on this bottom oxygen, and we can push them into that protonated carbonyl to get rid of that positive charge. Oxygen doesn't want to have that positive charge on there. It's electronegative. So we can draw a resonance structure. Now, all the oxygens satisfy the octet rule. Let me just put this lone pair here. Right, that top oxygen may have a positive charge, but at least it satisfies the octet rule. So don't freak out as though that's a carbocation. That's a different story, a carbocation, which only has 6 electrons. So I've got these 2 resonance structures. You know, every oxygen atom and carbon atom in here has 8 electrons, so they all satisfy the octet rule. That's pretty good. But it's not so good to have positive charge on oxygen, but at least there's this resonance stabilization for that. Now, let me show you why we never, ever, 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 ever protonate that bottom oxygen. Not ever. Let me go ahead and draw that out. If I'm telling you never, why am I going to draw it out? Maybe it's, I'm scared. You're going to see me drawing this out and only remember the thing I tell you to never do. So I'm a little bit scared about that. Look at those lone, there's 2 lone pairs on that bottom oxygen. You might think, oh, I want to protonate there. Don't ever, ever, ever. We call this the carboxyl oxygen on the bottom. And the one with 2 bonds, we call the carbonyl oxygen. We have different names for those. So you might have never heard that this is called a carboxyl oxygen, and the top one is called the carbonyl oxygen. Let me just make a note here. When should you protonate that carboxyl oxygen? Never, ever. And I have to say never, ever because you're going to try to do it because it looks like an alcohol, and you're used to protonating alcohols. You're used to protonating water. So you're going to try to protonate that, even though I'm telling you that the time you do it is never, ever. So I don't know how I can emphasize that enough. Let's go ahead and draw this hideous looking thing that you generate. It's just crazy looking. I shudder to draw this. It's just crazy. And so you end up with this oxonium ion right next to a carbonyl. Oh, what an awful place to put. And the reason why this is an awful place to put a protonated oxygen is because the most important resonance structure that you can draw for a carbonyl compound, and you're going to be drawing these resonance structures for carbonyl compounds a lot in the later chapters. The most important resonance structure you can draw for any carbonyl compound is to take the pi electrons and give them to the electronegative oxygen atom. That's a super important resonance structure. And when we get to later chapters, we're going to be attacking carbonyl oxygens because there's like 1/4 of a positive charge on that carbon. And so when you start to draw these extra resonance structures, you realize that kind of sucks to have 2 positive charges right next to each other. Boy, vaguely you're going to remember back in nitration reactions that we drew this protonated form of nitric acid where I had 2 positive charges right next to each other. And I told you, don't ever do this again. This is just crazy, having 2 charges next to each other. Whoa, this is, what do I do here? I'll just write crazy. That's crazy. Who would want to, if you had a choice to protonate the top oxygen versus the bottom and end up with this situation, nobody wants to end up with that situation. Don't ever protonate that bottom oxygen. You'll end up with this crazy situation. So get ready to protonate carbonyl oxygens, ketones, aldehydes, esters, amides, carboxylic acids. I promise you, you're going to see that over and over again. Resist every single urge you have to protonate that carboxyl oxygen on the bottom. Let me just give these names in case I use those names again. That's called the carboxyl oxygen, carboxyl, and this is called the carbonyl oxygen, carbonyl oxygen. So we have names for those. I'm not sure the book uses those names. I'm not sure if I'll ever use those names again. Okay, so what is this chapter about? It's understanding the acidity of OH compounds, carboxylic acids, phenols, being able to draw resonance structures of the phenoxide anions, the conjugate bases you generate. Whenever you make compounds that have charge, either a plus or a minus charge, they become water soluble. So deprotonating a neutral carboxylic acid, the neutral form would be soluble in organic solvents. The deprotonated negatively charged forms would be soluble in water, which is important for medicines, for drugs, for doing extractions in the laboratory.